Okay, hello and welcome. This is week 6 of SOC 224, Methods of Social Research. This week we're going to take a bit of a different style with things. This week we're going to follow the textbook quite closely, so I really do encourage you to read that. And this week we're not using the method that I used before with the PowerPoint slide, with the mind maps and so forth. Instead, I've got some PowerPoint slides. So I'll be interested to see whether you prefer these or not. These are sort of an old way that I was doing it before. They're quite pretty, actually, I think, anyway. So before we get started, a couple of things. In the textbook, there are some typos. So they're on the slides. You can look at them. But basically, in the textbook, there's just some key typos that are confusing. So it should be non-randomly picked, not randomly picked. And then here, there's basically in this table here, where they're reversed. Wherever I've got it green here, they're the wrong way around. But this is the correct way around, right? So quasi-experimental has no random assignment. All true experimental has random assignment. And if it says post-test only, then it doesn't have a pretest. It says yes pretest in the textbook. So all those things very crucial to just double check, because I found them thoroughly confusing as I was reading through and checking this textbook when I first read it. Okay, so let's get on with it. Look, the experiment is a method that is incredibly heavily used in the true experiment in one discipline called psychology, though it is seen in other social science disciplines less so. And in psychology particularly, and actually for all sciences, it is in a sense, it's the template upon which all other scientific research tends to be done, especially from a positivist approach, right? So those who see the social sciences like the natural sciences, they tend to see the true experiment that we're going to do today as the ideal way to do research. And the archetype, I guess is the word, the archetype. And so everything else, for people who are like this, particularly psychologists, they see all other types of research as, which we'd call observational research, as somehow less pure, much less accurate, not really science in lots of ways. So, I mean, I'm overstating a little bit, but probably not. In some ways, I'm probably understating it. Anyway, so the experiment is the true model of, from this perspective, the archetypical model of a scientific research. And at the core of a true experiment is this quite amazing and remarkable phenomena, which if you're not amazed at it, you probably don't understand it. And that is the fact that true experiments have what we call random assignment into the control and the experimental category. We're going to do this again later on, but if you think about when you do a survey, you may ask some low-wage workers, have you had a particular type, have you been paid in cash, right? And then you find that those who are paid in cash, which is your independent variable, and you find that those who are paid in cash turn out to also be more likely to be paid below the minimum wage. Great. And that suggests to you a causal relationship. But the problem you have is that those two groups that you're looking at, those who are paid in cash and those who are not paid in cash in your survey, they might not just be different because they are paid in cash. They could be different for a hell of a lot of other reasons. Maybe those who are paid in cash are actually more vulnerable workers generally. Maybe they happen to be international students or 1,000 other things. Maybe some different psychological variable. So what we say here in an observational research, which is the contrast to true experiments, in observational research like your survey, the researcher does not randomly assign the independent variable, or they don't get to assign the independent variable. Your independent variable being paid in cash is assigned by history, society, the real world, but it's not assigned by you. And in this case, we are comparing two groups, again, those paid in cash and those not paid in cash, but they could be very different. And this creates a problem, which is we just can't rule out other alternative explanations when we have when we do observational studies. Let me sort of cut to the chase and give you I guess one of the ways to think about this, and which will if we had a true experiment, what we'd be able to do is to, which I don't know how you would do it, but you would actually randomly assign who gets paid in cash and who doesn't get paid in cash. So you take exactly the same workers and very similar workplaces, and you just have those that are paid in cash and those that are not. Again, the problem would be, I don't even know how you would do that, but that's actually the nature of a lot of research and why it doesn't open itself up to doing experiments. The reason a lot of research can't be done with experiments is because you can't actually randomly assign being like economic depressions, all right? You can't randomly assign economic growth. So in economics, they can almost never do true experiments. In sociology, we can't generally randomly assign the effect of, growing up for 20 or 40 years under a racist condition, or growing up for 20 or 40 years as a woman or a man, right? These are not things that can be randomly assigned to someone. And so experiments don't work for a whole lot of sociological, economic, and other, other scientific things. Another example, which is a classic, is we learned is astronomy. You can't randomly assign most or any independent variables in astronomy when you're looking at like causes and effects, because you can't touch the stars, you can't change them, you just have to see what happens. Okay, that's a bit of an introduction. What I was saying, that there's something magical about experimental research, which I guess I haven't perfectly covered yet. Let me explain that to you. That magical thing about true experiments is that we divide the two groups that we see, or multiple groups that we do analysis on. So say we have two groups, and one of them we show pictures of spiders. I hope you're not scared by spiders. Pictures of spiders. The other half we don't show. We show pictures of cute bunny rabbits, right? And then we look at their levels of anxiety afterwards, right? Or their levels of stress, or stress hormones in their blood, or whatever it is. Now, if we just took two, haphazardly selected groups and assign them, the spider or the rabbit, we would not know whether the anxiety that we measured later on is really caused by the spider, or if it's caused by some other effect. So we're presuming the spider makes people anxious. However, if we do this test and if we do this study, and what we are actually able to do is randomly assign people. So as people say, walk through a mythical door, we flip a coin, and they've got a 50% chance ending up seeing the spider, and 50% chance of seeing the bunny rabbit. Then if we do that with a big enough group, let's say we did it with a really big study, like 500 in each group, then it turns out that those two groups will have almost, except for a little bit of random variation, exactly the same numbers of women and men. They'll have exactly the same number of people with blue eyes and brown eyes. They'll have exactly the same number of people by each any ethnicities. They'll have the same average IQ. So on almost any variable, or actually not only on any variable you can measure, but also on any variable you can't measure, those two groups will be identical. And that means, this is a strange example, but if we found out in 1,000 years that 10% of us were aliens, actually, we're all just like green people below the skin or something like this, that were from a far off planet. If we found that out in 1,000 years, and those 10% of aliens are walking amongst us now, well, it turns out that if we did random assignment in today's population, there would be equal numbers of aliens in both those two groups as well, with some random variation. Now, why is that? It's simply because of the role of randomness, right? Because everyone has exactly the same chance of getting into each group, the randomness actually almost completely eradicates any difference between the two groups. That's remarkable. It gets us two groups where there's no selection bias, because what selected people in? Randomness, true randomness. And then we know that if we do something to one, say show them the spider, and do something to the other, say show them the rabbit, the difference is the difference between those two images that they saw. It's the only difference. Okay, that's a long explanation. Let me move on, and we'll get into the substance of this. So experiments use the same logic that guide experiments in biology or engineering. They are the strongest way to test causal relationships, as we've sort of talked about. So cause and effect. And the reason for this is that they satisfy, better than anything else, three conditions we need to demonstrate causality. And those three conditions are temporal order, so A happened before B; association, so A is correlated with B; and then no alternative explanations, right? So that there wasn't something else that caused both A and B, or yeah, that's the main type of alternative explanation. It turns out, just as an interesting aside, that when you are dealing with when you're dealing with these three aspects of causality, it is the hardest of these three is actually the last one, no alternative explanations. And it turns out when you're doing your study, you tend to focus on one of them, association. Why is no alternative explanations hardest to prove? Because ultimately it's proving a negative, and ultimately there are an infinite number of alternative explanations, and you just can't possibly rule them out. What we do in practice with observational studies is we rule out other competing theories, right? So we say, well, what are other reasonable explanations? And then we try to control for that. But it turns out with a true experiment, because we've randomly assigned to two groups, we actually not only rule out the theories we know about, we actually rule out every single other alternative explanation, which is unbelievably powerful. Okay, so what do you do? Like when you're doing comparison experiments, we tend to talk about the experimental group and the control group. The experimental group gets the independent variable, though we'll learn that's a little bit more difficult to, that's a little bit more complex than first seems, and the control group generally doesn't, but often gets something that's very similar to the treatment. Some sort of placebo. Anyway, you can do comparisons that are before and after. So I could I could have you do a test, and then I could give you a treatment, like teach you the lesson, and then I could get you to do the test again. That would be before and after comparison. Or I could split the class into half and half, into 50 people, two lots of 50 people, and then I could teach half the class and not teach half the class, and then get you to do the same quiz. These are some very basic elements of any experimental design. When you do an experiment, the three things you do is you start with your hypothesis about what you think is happening, what the cause and effect relationship is, and then you modify or introduce the situation. You introduce the independent variable, and then you compare the outcomes. The outcome is the dependent variable. Okay. It turns out that certain types of questions are more amenable to experimental methods than others. They need to be simple. You actually need to be able to isolate and manipulate the causal mechanism. So that's why it can't be done in experiments generally can't be done in economics or in large societies or in the planets and stars. And often you need to target it on 2 or 3 variables in a very narrow scope. It's also so limited by the practical and ethical aspects of the situation, right? So there's only so much you're really allowed to torture people that is ethical, and which is very mildly, basically. And so these sorts of questions are great if you're doing psychology, for example, because you can put one person in a room, show them a couple of different things, see how it changes their brain and see how it changes the outcome. All very simple, right? But it doesn't work in lots of other situations. And this is why, for example, at the right opposite end of the spectrum to experimental methods are things like anthropology, where they will go and do field work and go and live with people for a year or two, a community. And in that, there are infinite number of variables taking place. There is no ability to isolate causal mechanisms generally because it would be unethical and impossible. And there's not a clear, simple logic to it. So I want you, as you're listening and thinking about the experimental method, to also keep in mind right at the other end of the spectrum to experimental methods and the sort of methods we've learned is things like fieldwork and qualitative methods, where the questions are vast, the variables are not even clear, there's not really the ability to isolate causal mechanisms, and often you're in a more exploratory stage of research. Okay. So I've sort of explained this, but here's a reminder about why we do random assignment. Random assignment is basically sorting participants onto 2 or more groups with a random process. Again, remember, random here does not mean haphazard or convenient. Random means truly mathematical. And with like a random number generator or a random number table and things like this. Sometimes it's not possible to do random assignment, so a very close, or you can actually do this or combine with it, you can do a very similar thing which is called matching. So if you, for example, in some medical studies where you can't do an experiment on a large number of people, what you will do is you will match the participant who gets the drug and the participant who doesn't get the drug, for example, the treatment and not get the treatment. Not only will people be randomly assigned to particular conditions, but they will also be the same age, the same gender, and maybe a few other really key characteristics, like the same, like they've both either not got a medical history or have a medical history, etc. And by doing that matching, it's another way of very explicitly the researcher making sure those two groups, the control and experiment, are as identical as possible. So what are the key concepts we need to use here when we're talking about experiments? So some keywords. The independent variable, that is the variable we've already talked about a lot, but it's a variable that is causal, that is seen as the thing that changes the dependent variable. It's the predictor of the dependent variable, all those sorts of words. And the independent variable is what the experimenter can manipulate. They change. And the independent variable changes first, the dependent variable changes after that, if your experiment is correct. The dependent variable is the outcome, and yeah, it's the effect, it's the change that you expect. So in our previous example of being shown spiders and bunny rabbits and getting anxiety, the independent variable is the spider, the dependent variable is the anxiety. Now, in many experiments, you have something called a pretest and a post-test. The pre-test and post-test are measures of number 2, the dependent variable here. So they're measures of anxiety. This is another test you can do. So if the random assignment has made particularly different groups, this is another way to rule it out, because we don't know what happens with randomness, right? So the pre-test measures the level of anxiety in those two groups, say of 500 people. So 1,000 people, we measure each of their individual anxieties. That before we show them the spider and bunny rabbit, that is the pre-test. And then the post-test is the true measure of the independent variable, where we just do the same measure. We measure their anxiety again after the independent variable has been introduced to the experiment. And so that pre-test adds what, in most experiments, another control. Some other key concepts, the experimental group. So those are the ones who receive the independent variable, or as we'll see, sometimes independent variables are continuous. So we'll say there who receive the independent variable at, say, a high level. So they see the spider for a long time if we varied the amount of time people saw the spider, or they see a really scary, realistic picture of a spider. And then we have the control group of those who don't receive the independent variable, or receive a low level of it, or receive a placebo. Placebo we'll learn about later, but a placebo is something that it's basically a fake treatment. So if you've been given, testing antidepressants or testing anti-anxiety medication, the placebo would be a pill that's a sugar pill. And the point is that the participant can't tell the difference. And you also have the other concept we've talked about is random assignment, which happens right at the beginning. Okay, so what we're going to do is start off by watching a video about an experiment, which we've actually already talked about. We learned about it in ethics, and I've got a replication of it, a really exciting replication of it. If I was teaching this in class, I would get one of you to summarize it, but I am not going to. What I'm going to do is I'll briefly summarize it, show you a table, and then we'll watch a real video of how this takes place. It's a 10-minute video. We'll watch in this video so that you can just watch along with me, and then we're going to do a quick exercise of sorts, even though I'm going to be doing it on my own in my house, but you get what I mean. I'll give you a few minutes to pause it and think it through. So, what's Milgram's experiment? Milgram's experiment, this is you've just to scroll back, you have seen, this is the book for it, the experiment that changed human nature, a classic account of how human beings obey orders, and the frightening things that happen. Basically, in this study, we have 3 people, but actually only one of them is a true participant. The others are what we call confederates. So what we have here, the true person being experimented on is the student, and we have the experimenter, and we have the learner, who's labeled with an A here. And the way it works is that A and S, so the student and the fake participant, come into a room, and they're basically randomly assigned, or they think they're randomly assigned, but they're not really, to either be the student or the participant. And then the experimenter says they're doing a memory test where the student is going to read out a list of options that the participant has already, but they're not really a participant. The participant has already, or the learner has already been read, and the student is going to test their memory. And the experiment is supposed to be about memory and learning under conditions of stress or pain or such. what happens is, as the learner gets more and more of the questions wrong, which they will, and it's just a recorded voice, the student will give them higher and higher electric shocks. The experimenter will urge them to continue, and eventually the student either stops giving the electric shocks because they become so morally outraged and about the experiment and worried about the learner, or the student continues to the highest voltage. So that's the summary of the experiment. The big thing that happens in the experiment is that when Milgram did it, two-thirds of the main one, two-thirds of students went to the highest possible voltage. And this included after they heard through the learner being in another room and a fake voice, but you heard the students thought they heard the learner screaming, yelling, demanding to be released, saying they had chest pains, and then going silent. And still, despite this, 66% of students went all the way to, I think it's 450 volts or such. Okay, that's the way it's traditionally told, but actually, Milgram repeated the experiment under many different conditions. So that first one's called Experiment 1, initial study at Yale University, men and women, 65%. But he also had all these other different variations of the experiment. So he conducted one off campus, so it was a less prestigious environment, and only 50% of people, 48% of people were obedient to the maximum 450 volts. In Experiment 3, they put the teacher and learner in the same room, and in that, only 40% went to the maximum. In Experiment 4, they made them hold the shock pad, only 20%. And they basically go on up to situations like where the teacher chose the preferred shock level, or the experimenter indicates the participant could not shock. And basically what it shows here is that depending on the social conditions, the amount of obedience changes a hell of a lot, right? And these represent later situations where there's less rigid and authoritative forms of authority, or reputable forms of authority. And as there are less reputable forms of authority, it turns out that the percent of obedience goes down. Okay, let's watch the video, and I want to tell you what the question is. The question is going to be, in the video and in the description I've just given you then, identify the 7 elements of a true experiment: independent variable, dependent variable, pre-test, post-test, experimental group, control group, and random assignment. Okay, so let's watch the video. I will bring it up here now.
There are 9 subjects left. I can only use 4 for the heist, so a week after the seminar, I arranged to test the limits of their responsiveness to authority. So, a week ago, I arranged for them to take part in what they now think is a piece of unfilmed academic research at a university, and nothing to do with the show, supposedly looking into the effects of punishment on learning. And they believe now that this is part of their growth. In fact, it was a reenactment of a powerful experiment conducted by Stanley Milgram in 1963 to look at how normal people can commit atrocious acts simply because they're following orders. Milgram's parents were Jewish refugees in World War II, and his pioneering work speaks volumes about the nature of responsibility. It's being filmed with covert cameras.
Thank you.
Lovely. Come in.
They're introduced to an actor pretending to be another participant.
You didn't come from the same room?
No.
Yeah, you don't know each other.
No.
But we don't actually know how punishment affects learning.
After a brief introduction, our subjects are tricked into thinking they've chosen their role as teachers in the experiment.
And if you could just tell me what your positions are?
Learner.
Learner and teacher.
Learner.
Teacher.
Our subjects observe the learner being instructed by the scientist, who is just another actor.
This electrode is connected to a generator in a second room. We might be going with the teacher.
Okay.
Just make sure that we have a good contact with the skin so it doesn't cause any blistering or burning. Is that comfortable?
That's okay, yeah.
Yeah, we just place these straps around your arms just to avoid any excess movement. Those aren't too tight.
No, that's okay.
No. The teacher will read out some word pairs to you. Blue girl.
The learner is told he's going to be asked a series of memory questions by the teacher. He will have to word pairs and then correctly remember them when offered multiple choices.
If the answer is incorrect, you will receive an electric shock.
The teacher is then taken next door and shown the generator, which ranges from 15 volts all the way up to a lethal 450 volts. The domestic electricity supply in the UK is of course 240 volts.
Your job is to read
Our teachers are given the list of questions and told to increase the voltage each time the learner gets a question wrong. They are then given an example of a low voltage shock.
and try and estimate in volts the amount of shock you feel you're getting.
Okay. Oh, shit.
Do you know how much that was?
Enough.
75.
It was actually 45. Just down here.
Oh my god.
Teacher, begin.
Shoe horn. Steam.
The point of this test is to see whether the teachers, our subjects, will call a stop to the experiment or continue to the point where they are administering seemingly lethal electric shocks to the victim simply because the scientist is telling them to.
That's correct. The next word is bicycle. The options: tyre, race, helmet, shorts. That's incorrect, so there'll be 120 volts. I don't think I want to do this anymore.
If you could continue, please, teacher.
There is... No, I don't think I'm going to do any more.
Well, the experiment requires you to continue.
Yeah, even so, I don't think I'm going to do any more.
Correct. Captain.
According to plan, our accomplice provided many wrong answers. Each protest was coordinated to a particular shock voltage on the generator, and his responses were played via a CD.
That's wrong, 150 volts. The correct answer is Captain Shoe. Cup. That's wrong. 225 volts.
Take it off! I've had enough of this!
He's in a lot of pain,
Continue, please.
but he's not comfortable.
We must continue to the end of the experiment. Whether the learner likes it or not, he has to go on until he's learnt the words correctly.
Okay. Forest. That's wrong, 240 volts. Are you sure this is not causing any lasting damage? He sounds like he's in a lot of pain.
Well, the shocks might be painful, they're not harmful.
What does that mean, though? They're not harmful. Sorry, I'm not getting you. When you say that they might be painful but not harmful,
They cause no long-term damage.
okay, so what does that mean? That it doesn't leave any scars?
It causes no damage.
That seems very cold and calculated to me. This doesn't seem like a very... Anyway. Golden. That's wrong, mate. 300 volts.
Ow! That's enough! I refuse to answer anymore! Just let me out!
Staple. The options are diet, jar, balcony, and bowl. Who are we going to answer?
If the learner doesn't answer in a reasonable time, say 4 to 5 seconds, then you have to treat the answer as wrong and follow that procedure.
Did you hear that, learner? Just any response, mate. Come on. Wild guess.
Please continue.
345 volts if you're still with me. I'm sorry. I can't do this, honestly. Can we stop this experiment? Because I can't do this.
If you don't continue, we'll have to discontinue the experiment.
Yeah, okay, fine. That's fine. I'm not going to do this.
Incorrect.
405 volts. Sorry, I don't know, does someone want to check on him or something? It's just he's not making any noise now, and he was before, and I'm quite happy to go on, but I'm just a bit worried about...
If you would continue.
Yeah, I'm just a bit worried because he was... Like, he was, like, complaining before about the...
But no harm will come to him.
But he's not making any noise now.
It's essential that we continue with the experiment.
Balcony. Incorrect. 450 volts. You promise he's not... It won't...
Please continue with the procedure.
You say it hurts, but it's... Because it's like... It says they're dangerous in a shot. It'll be alright, yeah?
Please continue. Okay, I think we'll discontinue the experiment there.
All of the subjects were told the true nature of the experiment was to see how they would respond to authority, and that it would eventually form part of this show.
He is okay.
I can tell you, he's absolutely fine. You actually weren't administering electric shocks to him at all. He is.
In the original Milgram experiment, psychologists were asked to predict how many people would continue to the point that they were administering the highest shock on the board. Their prediction was 0.1%. They were wrong. The results of our experiment were almost identical to the original. Over 50% of participants continued up to 450 volts. The majority of people will administer lethal electric shocks just because a guy in a white coat is telling them to.
450 volts.
450 volts.
450 volts.
450.
So after the results of the Milgram experiment, I've now chosen my 4 subjects that will go forward for the heist.
Phil was impressively resourceful when he was caught stealing sweets, and held in his anguish during the Mildred than Defy the Scientist. I did want to include a woman in the group. Jen was the only subject to take a long time to recover after the Milgram experiment, so I felt I shouldn't use her. Veronica didn't steal from the shop, so that left Vicky. Of all the subjects, she was the only one to have known the original Milgram experiment and call a halt to her involvement in it.
Can I just say, I can't do this because I've heard of this experiment before.
So I think she'll be quite interesting to use, although I don't know if she'll actually take the bait or not.
Ali stole most from the shop, seems to be highly responsive, most outgoing, and seemed most happy to continue the experiment until he was stopped.
Well, shouldn't it have made more notches on the thing?
I'm sorry. Danny stopped the experiment, but in such an outspoken way that I suspected he would have real strength of character to bring out.
It's not even reacting anymore.
Okay, so that's the end of that. What I want you to do now is just pause the video and just take, 2 minutes, 5 minutes, whatever it is, to just write down examples from that video and also from the examples I've given you before, what the examples of each of these 7 different elements of the true experiment. Okay, pause now. All right, you're back. So let me go through it very quickly. Most people will get this wrong. It's actually quite a trick question. So we can talk about the independent variable and dependent variable. I should say I want you to try to identify them at a conceptual level, at least the dependent and independent variable, and also at an operational level. So let's talk about those. The independent variable, the dependent variable, let's start with the dependent variable. What's the dependent variable and how is it actually measured? So the dependent variable is clearly, it can either be, does the participant get to the maximum voltage? So it's binary then. So if we look back at this slide, this is a binary outcome of how the voltage, but actually what is the concept behind it? Sorry, that's the operational definition. What's the conceptual definition? Well, I think it is basically obedience. It's following orders, as it's put in this table here, obedience, percent obedience. So the dependent variable is obedience. The independent variable is something like authority or legitimacy of authority or strength of authority, because it's like, but yeah. And so what we see is how much does authority in its different forms lead to different levels of compliance. The dependent variable can be measured in a binary way, as whether you get to 450, but also can be measured as a continuous or interval level variable, maybe even a ratio level variable, because you could say what level does someone go up to. So it could be that they go up to 20 volts or 150 volts or 300 or 450 volts. So the dependent variable can be measured in both ways. How is the big question, and this is the one that everyone gets mistakes and gets wrong, is how is the independent variable measured and manipulated, operationalized? So we know its level of authority. It turns out in the version of Milgram's experiment, which most people get told, there isn't any change. It's actually kind of a one-shot experiment we'll learn about later. But if we look at this table here, these are the different levels of the independent variable. They're different levels of basically authority or legitimate authority or authority which cannot be defied. And notice that it's actually kind of categorical. They are ordered, but now they're basically ordered by the dependent variable, which is not really a proper ordering. So really what we look at here is a categorical set of independent variables that have very different situations where authority is like more or less strong, more or less legitimate. Okay, pretest. A pretest would be a measure of the dependent variable, which is how high you're going to shock, before you give the independent variable. Well, there's not one of those in this. You don't pretest on the particular students. You might, and the post-test is simply what level they get to on the dependent variable. Either do they get to the maximum or what voltage do they get to. What are the experimental and control groups? Well, it turns out, again, there's not a clear experimental or a clear control group. All of these are different, I guess, experimental groups that receive different levels. You could argue that maybe this last group where there's very low obedience is one of the is a control group because it has the lowest level of the independent variable, the least authority, but really they're just a whole lot of different experimental groups, and there's not any particular control group because it doesn't really make sense. The last one, and this is where it's going to be where you might have been confused as well, is what's random assignment in this? Where is the random assignment? Now, most people will get this wrong and they will say the random assignment is when the student and the learner came into the room at the beginning and were randomly assigned to whether they were student or learner. But actually, the truth of it is that was fake. That was completely faked. The other person is a confederate, and so it looks like random assignment, but it's just fake. And actually, we didn't really hear about random assignment. In the video, there wasn't random assignment, and here we could perhaps assume, though there might not have been, that there was random assignment into each of these groups. Though my guess is that Milgram didn't bother with random assignment. He probably did one study with a particular setup, then another study with another setup, then another study with another setup. But if he had have randomly assigned people to these different, like how many are there? There are at least 17 experimental conditions, then that would have been random assignment. Okay, I hope that exercise was useful to you. Let's move on. So, do you speak the language of experimental design? Again, right? So there are different types of experimental design. We've sort of talked about that. There are independent groups where we measure across on two or more different groups. And there's repeated measure designs where we measure the same variables on the same group. So independent groups, again, is like if I divided the class in half and gave different treatments to each side of the class. I taught one half and didn't teach the other. I used experimental with one half and a very more normal method of teaching with the other. And a repeated measure design would be if I, measured you each week and then I varied the teaching style and looked at how much you'd learnt or didn't learn. I think this slide is straight from the textbook. I don't think it's that relevant, but anyway, what it says, it just goes through the steps that you go through. So you choose a hypothesis, you design the study, you decide how to introduce the independent variable, you make sure the dependent variable is measured validly and reliably, you set up the setting and conduct a pilot test, you locate appropriate participants, you randomly assign them to groups, you gather the data, you introduce an independent variable, and you gather data for a post-test, debrief the participants, and then examine data collected to make comparisons between the different groups. I guess it's a good recipe. Hopefully, maybe you'll find that useful if you decide to build an experiment into your study, which you still could actually. Just to say, one of the ways you build an experiment into your study for this class is if that you actually had, for example, 2 different versions of the survey, and you wanted to try out, say, 2 different treatments to see whether people responded. So, for example, you might say, we are going to offer half to join a union and show them a leaflet, and then we're going to offer half to join a union, but we're not going to show them a leaflet. We'll just give them a very boring definition, and we'll see whether there's any difference in whether they actually click the link to go and join a union or indicate that they want to join a union or not. That would be an example of testing between different recruitment methods. You could say sort of similarly, you could give them information about what's happened to them or not, and then see whether that changes their likelihood to report to Fair Work. Okay, so do you speak the language of experimental design? Let's keep going. So when we do an experiment, we need to isolate the independent variable. So basically make sure it's not some other confounding thing that's changing, a variable that's changing things, eliminating alternative explanations. One of the ways we do that is what people who are called confederates. Confederates are people who, they're basically just paid research assistants, but they are generally people who are doing some fake role. They're pretending to be something else. So in a famous experiment, there was one where they asked people, how are these 2 lines the same length or different lengths? And you had 7 people sitting around answering whether they thought it was or not, but actually only one of them was the true participant. The others were actually saying fake answers that they were told to say by the researcher. They would be examples of confederates. One of the reasons we use confederates is often, it's to create a very realistic scenario, and often it can also, the confederates may or may not know what the true experimental design is, so that can reduce the impact of the experimenter, the researcher who's got a real vested interest in the outcomes of the results, from actually participating, or from actually affecting the results, by participating. The experimental design is just how we arrange it, and the key thing here is that a true experimental design or a classical experimental design means a very particular thing here. And the key element of a true experimental design is the use of random assignment. So there's 2 words, true and classical. Classical has all 7 of those elements we talked about before. A true, particularly random assignment, control and experimental groups, pretest and post-test, and dependent and independent variable. A true experiment must have the random assignment and multiple groups. It doesn't necessarily have to have anything else, but true experiments are defined by having random assignment. So this is an example of a classical experimental design from the textbook. So we're checking whether people get more tips or not. It turns out that this is really relevant, because if you go to a half-decent place that does table service, then you will almost always have this, there's a couple of phenomena, right? One is that the person will introduce their name, and the other thing is that they will also, after you have got your meals, before you have finished your meals, they will come back and check. So there's a burger place just near Macquarie. It's sort of like, so it has all healthy burgers and vegetarian burgers, and they actually have a little stick that's got 2 ends. One's white and one's red. And I think white means you haven't been checked and red means you have been checked. And after they bring you the meal, about 3 or 4 or 5 minutes later, they will come back and they will flip the orientation of that little stick that's on your table, and to say you've been checked, and I will ask you, how is the food? I understand that this is because it is these 2 things, self-introduction and returning to check, are incredibly effective ways of making happy customers. They're probably also ways of making sure that if anything has gone wrong, you can deal with it before it's too late. Anyway, so this is a test of that. What they do is, so basically what we have is that down here, group 2 is the control group, and group 1 is the one that receives the treatment. But in the first month, they're both treated exactly the same. They both serve food without introduction or checking, and we measure the amount of tips. That is our pretest. And then in month 2, we change what happens with the independent variable. We do with group 1, we actually have them do self-introduction and checking and measure their tips, while for the group 2, they remain the same. They are the control group, and we see whether their tips change. And this is good to check that it just hasn't in month 2 become Christmas, right, or become January or something like that, when there's very big differences in tips. And also to make sure that group 1 and group 2 are actually very similar here. Okay. This is one where we only have a post-test, so we don't have the pre-testing, and we don't have a measuring of the amount of tips after month 1. So it's a post-test only style. This is called a Solomon 4-group experiment. It is basically what we do is it's the Solomon 4 group. The key thing here is at time point 1, we measure the amount of tips only in half the groups and not in the others. It turns out that with experiments, many times they can be biased simply through measurement. So this is to check whether the pretest or the measurement actually leads to a change in the final outcome. So, if these two, like this one here, independent variable retrain, should be the same as this one here. And this one should be broadly the same as this one here if we've randomly assigned. But if these two are dramatically different to these two, then it would suggest that there is some effect of the actual pretest. Fine. Latin square, it's a method of doing experimental design where basically you change the order of the treatment, so you make sure it's not an ordering effect. So here you take the order and do introduction after they finish the meal. Here you do the introduction, check on the customer, and then offer dessert without them repeating the self-introduction. And you're looking to see whether there's any ordering effect about when the introduction is done on the tips, which there might be actually. It probably is nicer to introduce yourself at the beginning. So some other language or concepts that are really important to get are factorial design. So factorial design would be when you have multiple different treatments and you want to see whether the different ones have particular differences. Often those other independent variables might not be randomly assigned. So a factorial design might be, I'll give it a simple one, like we're saying whether you would join a union or not. That's the treatment, but we might also do it by men and women and by whether they suffered some sort of mistreatment at work or not. Right, and that becomes a 2 by 2 by 2, because effectively there are, if we multiply 2 by 2 by 2, we get 8. It turns out that there are 8 different conditions, but you can think of it as a 2 by 2 by 2 cube, where we have, did you get offered to join a union or not? Are you male or are you female? Presuming binary variables. And are you, did you suffer mistreatment or not suffer mistreatment? That would be an example of a factorial design, and we would have then 8 different potential 8 different levels of the outcome for each of those different situations. We can also talk, and we're not going to do a lot on this now, but about main effects and interaction effects. A main effect is the concept that let me give an example. Like if we're looking at, say, we're doing it as a 2 by 2, men and women by experimented where this is offered the union leaflet and not offered the union leaflet, right? The main effect would be the main effect of being offered the union leaflet, or the main effect of being, say, female. That is the effect, the amount that the joining a union goes up because of that particular effect. An interaction effect is complicated, but it's basically if there's an additional effect for, say, being a woman and offered the leaflet that is more than just the effect of being a woman and the effect of being offered a leaflet, then this would be called an interaction effect of gender and being offered a leaflet. That's complicated. If we have time, we'll be dealing with it later when we're doing analysis, but we don't really have time now. Here we go. So this is an example of the food and checking. So they start off without food and checking. We have a male and a female group, and then we are measuring the levels of when we actually retrain half of them to actually do the return and check on the customer, and we measure the tips. We'll deal with more with that later. You can also Google it or read more in the textbook about main and interaction effects. Okay, so do you speak the language of experimental design? Yet again, another concept is pre-experimental designs. I just want to notice this language being used pre-experimental, we're going to use quasi-experimental, etc. are examples of the bias built in towards experimental design in this language, which really comes from psychology. But what are these pre-experimental designs? We'll just use the language. they lack one or more parts of the classic experimental design, often many more. So we could do a one-shot design, case study design. This is where, well, actually, we'll see some videos of this, but they would be examples where you simply do a study once, you just do something once. Most of those pranks, actually, that we looked at, if they were real, were examples of one-shot case study designs. They kind of illustrate something. For example, the Milgram is a one-shot in many ways because they simply have one, the first Milgram one where they get to the 66% obedience. That is a classic example of a one-shot. Why? Because there's no variation in the independent variable. There's just the guy in the lab coat, one level of the independent variable. And what do you get at the end? You just have one measure. But no, the one-shot post-test is really effective at showing something, even though it's got virtually no other control conditions and like no other it has no other what do we call it? You would have no controls, no other levels of the independent variable. Why is it important? Why is it powerful? Because we didn't expect 66% of people to, basically kill someone for an experiment, right? Because they're told by a white lab coat. So one-shot case studies, that's an example of a one-shot case study, and they can still be very effective, especially when they contradict what we would think is going to be the outcome. One group, pre-test, post-test, very similar. Static group comparison. So this is basically where we compare two groups, but we don't randomly assign them. Quasi-experimental designs are very similar. Generally, the difference is quasi-experimental designs. The key thing that quasi-experimental designs are missing is the random assignment. So some of these pre-experimental are actually missing more than one case study group. Whereas with quasi-experimental design, we at least have multiple comparison groups, but we don't randomly assign. So this actually applies. Quasi-experimental is used to refer to correlational research and almost all survey research, basically. That's the way psychologists will refer to it. This is a comparison of experimental designs. So we have these different, you can go through it yourself, but note there is no random assignment in pre-experiments. And except for the static group comparison, we don't even have a control group. Actually, see, this is the wrong, this is wrong. Oh no, this is correct. Actually, I should say this one is correct. This is correct. My fault. But so there's no random assignment. In the true experiment, we have a random assignment. That's the key difference. And then with a time series design, we can see here we don't have random assignment, but we also don't have a control group. Why don't we have a control group in a time series design? Because we're doing it on the one group over time. We just have an experimental group, but because we vary whether we give them the treatment at one time or another, there's no control group, right? There is this thing called design notation, which you can use. It's a symbol system to express a design. It's basically, we use O to represent observing the dependent variable, X to represent giving the independent variable, and R to represent random assignment. I just want you to sort of know that this happens. If we take a look here, these are some different ways of drawing it and expressing it. So the classical experimental design has random assignment into one of two groups, which we then observe the independent variable. We give the treatment to one of them, and then we observe the dependent variable again, right? In a one-shot case study, we only have one group, and we just have the treatment and the outcome. The pre-test, post-test, we have the same thing, but we do a pre-test. And with static group comparison, we don't have any random assignment, we don't have any pre-observation, but we do have the treatment and then looking at what happens. A lot of natural experiments end up following this form, actually. Okay, we're nearly at the end. Let's just go through a few really important concepts, and we're going to get a bit more in depth on that concept of validity. So we dealt with validity in week 4, where we did measurement. Let's deal with validity now. Again, this time we're going to draw a distinction between two types of validity. One's internal validity and the other one's external validity. Internal validity is basically the idea that, or something that is internally valid is the idea that you can't be sure, is internally valid if you can't be sure that the cause actually was the thing that changed the effect. So that there is some sort of breakage of the linkage between the cause and effect. I'll give some examples and it will become clearer. So yeah, what does it say here is the definition? The ability to state the independent variable was the one sure cause of the dependent variable. If it's not, then there's some spurious example. So these are some examples of threats to internal validity and some interesting stories. So the main one is selection bias, which means that somehow you thought you would divide them into two even groups that were similar, or that they were similar groups, but actually there was some sort of selection into one group and not the other. So my dad used to tell me this story when I was young about a screwed up experiment. Apparently after World War II, it was all the rage across the world, to especially developed world, but to give kids milk. The idea was that they had found that kids who drank milk and societies that drank milk tended to be taller and stronger and healthier and so forth. So what happened was that, but in Britain they wanted to test this, and I think in Scotland they had a study where they went to where they basically wanted to test whether it worked. So they gave enough milk for half the kids, right? And what they did was they measured their height before they had started on the treatment. Then half the kids at the primary kids at schools got the milk, and then at the end they measured them again. What they found actually was that milk made people grow less. And this was, of course, very surprising, but it was because there was a selection bias. What had happened was there wasn't random assignment to the two groups, or even if there was, it wasn't followed. The teachers instead said, well, we should give the milk to the kids who need it. And teachers tend to know which kids are underfed or not getting proper meals at home. And so what did the teachers do? They gave the milk to the kids who are basically malnourished. And those kids did see less growth because of the crappiness in the rest of their lives. But the milk generally probably did have an effect. So again, that's an example of completely screwing up a study because of a selection bias, because you had teachers who gave the milk to the kids who needed it. But also it's probably an example of an unethical study because they would have been denying a whole lot of needy kids milk. But anyway, that's what happened. Okay. Another example of a threat to internal validity is history. So if you did a study before and after that had some of it done before and some of it done after the 9/11 attacks, or some of it done before or after, say, the shootings recently in New Zealand, you could get very different results from the people who did it before and after, and it has nothing to do with the experiment at all. Instead, there's something, the world is changing around it. Another way that you can have a threat to internal validity is maturation. So I could think that because I teach you, you all become smarter, but actually maybe you're all getting smarter because you're just getting older and your brains are becoming more mature. This is definitely the case with respect to much of education over the period from, birth through to year 12. There's a huge amount of growth, and a lot of the learning, what's ascribed to teaching, is actually partly maturation. Though it's not all, clearly. Only a part of it is. As we've talked about, the testing could affect it. So we do a pre-test, and actually the pre-test, because people are getting attention, they start to pay more attention to what they're doing, and they realize they're being experimented on, and that sort of changes it. We could have mortality. It doesn't have to be death, but just dropping out of the experiment. So if we give people a treatment and the treatment gives half of them diarrhea, and those people then drop out of your study, then actually it could really bias the final results. And then the other problem is contamination or diffusion. Now, these are all examples. There are more, but one is contamination or diffusion. So say I teach half the class how to study the topic really well, and I don't teach the other half of the class, but then actually the half of the class that I've taught is actually sharing groups with the rest of you, and they teach everyone else these techniques or these tips, then that's a diffusion from my experimental group to my control group, and it screws up my experiment. Okay. The other threat to internal validity is experimenter expectancy. So basically, just because I think I'm being objective, I often have an interest in the outcomes of the study, and I can bias it in various ways. This is one of the reasons why most experiments are conducted in a double-blind way. So generally, the experimenter is not the one who does the study. Instead they hire people, and they have assistants and so forth. The other way you can solve for experimenter and also for participant expectancy is placebos. So placebos are, so often if you do an experiment, say you showed someone that union leaflet and see what effect it had on recruitment, but you wanted to make sure it wasn't just reading that made people join unions, then you might get the other people, the control group, to read something else neutral, like read an ad by Macquarie Uni or read a leaflet by Macquarie Uni or something like that. Okay, moving right along. External validity and field experiments. So we talked about internal validity, but there's also this concept of external validity. So while internal validity is internal is about whether you can truly say the cause is the change in the effect and there's not something spurious going on. External validity is about how much you can say that the cause and effect relationship you saw in the experiment can really be generalized to the larger world, right? So note that most experiments are done, or many experiments are done in a lab with first-year psychology students, as we joked about, and a whole lot of other things. These are very artificial settings, and there can be a threat to external validity if you can't really generalize outside of that setting. So the participants might not be representative, the setting could be artificial, or the treatment could be artificial. You might say that, well, there's effective disgust on whether someone is right-wing or left-wing, and then you put them in a room and just show them some poop, and then you measure whether they're right-wing or left-wing. And this might not really be valid, and you may say that the people who are shown something disgusting become more right-wing, but does this really generalize to the entire population as a whole? Maybe, maybe not. And another example of this particularly, which we've already talked about, is reactivity, which is basically when you change your behavior because you know you're being studied. And the Hawthorne effect is a particular type of reactivity, where because you're aware of being studied and also the attention you're receiving from researchers, you change your behavior. So this is a classic example where it comes from this thing called the Hawthorne study, where they studied factory workers, and they found that no matter what, and they were trying to improve productivity, but what they found was no matter what treatment they did, productivity always improved, which was very, very weird. And what was actually going on was it was not like changing the lighting or changing the work setup or any of those sorts of things that was actually improving productivity. What was improving productivity was just the fact that people were being studied. And this is one of the reasons why we include things like the placebos and very realistic controls, so that you don't get the Hawthorne effect. Another way to deal with external validity, or problems of external validity, is to do things like a field experiment. So I'll give an example from my students' projects in previous years. The same group did a study of whether you would lend a mobile phone to or your lending of a mobile phone would change whether the person you were lending to was Chinese or Indian, because this was Singapore, with their expectation that people would be racist, basically. And so they did two different versions of the study. One they did online on Qualtrics, and they said, would you lend to this guy? And half of them got an Indian, half of them got a Chinese, and there was no difference. But then they went to the local shopping center, and they simply had an Indian-looking guy, he's actually Bangladeshi, a student and a Chinese student go up and each ask 50 to 100 people whether they would lend them a mobile phone, because their mobile phone has run out of batteries. And it turned out about 75% would lend to the Chinese, and about 30% or 25% or something would lend to the Indian. So what you have here is completely different results. The very artificial situation shows that you have no racism in this community and no difference, whereas the true experimental, whereas the actual field experiment, which is much more valid, has very, 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 very racist outcomes. So it's a good lesson in why you can't really trust things that are done in artificial environments. Here's a summary of those threats to validity. I think this is the second last slide. Yeah. So the last couple of points. So a version of a non-true experiment, like a quasi-experiment, that is used a hell of a lot, and actually we're going to deal with it more when we do historical research, is called a natural experiment. So this is things like where you couldn't really plan for something to happen, but it did, and then you use experimental logic. Examples of this, you might compare two countries where there was one had a depression and one didn't have a depression, and look at how that affected politics or life expectancy or such. We're going to look at an example in a couple of weeks' time where we look at examples of how the media in the US reported two different things. One which attacked the official enemy and one which didn't. It was a genocide done by communists and a genocide done by Indonesians who supported the US, happened at the same time, and they look at the media coverage in newspapers like the New York Times. That is an example of a natural experiment. You're varying whether the bad thing was done by an official enemy or not, or an official ally, and then looking at whether there was a change in some outcome. No, it's got all the problems of not having random assignment and particularly selection bias, but it actually has got a whole lot of advantages because it's actually taken from the real world, and so it has a lot more external validity. In practice, make sure you plan and pilot your experiments. Make sure you give really clear instructions to participants. And after the experiment, particularly if you use any deception, you need to do a debrief. So explain that deception was used and re-obtain informed consent. Lastly, deception, just a reminder, deception is acceptable if it's minimal and it's necessary and you've got approval, but dishonesty is not. Debriefing is a must. Okay, that's the end of the slides. I'm going to now just move on. I'm going to show you the experiment that I want, or the exercise I want you to do this week. And then I'm going to give you two choices of exercises, actually. And then I'm going to play you a series of videos which you can look through and use for one of the exercises. So these are a whole lot of really interesting examples of studies that have been done. Some of them are more real than others. Okay, just give me a second. So let's open up the exercise sheet. This is a slightly earlier version than the one that will be online, but so the first exercise with the videos, which you can do, is watch the videos and identify examples of each of the key concepts we've got this week. So the concept and then example. And then the second exercise is to actually go through and just do a simple design of your project or the hypothesis of your project using experimental design. So what's your question, your hypothesis, operationalization, and other details. For external students, you can pick either one of those. For internal students, we'll probably do both during class. Okay, what I'll do is I'll actually put up the videos separately so that internal students can watch the videos in class. Okay, thanks so much. See you next week.